On a warm summer evening in 1985, a Boeing 747 lifted off from Tokyo bound for Osaka, a route so routine that thousands of people flew it every week without a second thought. 4 to 4 minutes later, that same aircraft lay shattered across a remote mountainside. 520 lives lost. Just 4 survivors. This is a story of Japan Airlines Flight 123, the deadliest single aircraft accident in aviation history. It's a story of a hidden structural weakness, a desperate 32-minute fight to keep an uncontrollable jumbo jet in the air, a rescue that came too late, and the lessons that change aviation maintenance around the world. I'm Johnson, and this is what really happened on August 12, 1985.to understand Flight 123. We have to step back into Japan in the mid-1980s. These were boom years. The Japanese economy was surging. Factories were running at full capacity. Cities were expanding upward and outward. The overnight train still ran, but air travel had become the new symbol of speed and modernity. And at the heart of Japan's skies was one airline, Japan Airlines, JAL, founded in 1951. JAL was a country's flag carrier. Its aircraft were national symbols, painted in white with proud red crane on the tail, the Tsuru mark. By 1985, JAL operated some of the busiest domestic routes in the world. One of the most heavily traveled was a short hop between Tokyo's Haneda Airport and Osaka's Atami Airport, just about 400 kilometers, a flight time of less than an hour. And on August 12, 1985, one of those flights was JAL 123 to the aircraft assigned to Flight 123, was a Boeing 747 SR-46, registration JA8119. SR stood for short range. This was a special version of the classic Boeing 747 designed for busy domestic routes, especially in Japan, where airlines needed wide-body capacity for short flights. The 747SR didn't look much different from a standard 747, but it was built to endure many more takeoffs and landings, more cycles, than its long-haul cousins. JA8119 had flown thousands of these short sectors over the years. On the surface, it was a workhorse, reliable, familiar, almost ordinary. But hidden deep within its structure was an old wound, one that had been slowly worsening with almost every flight. 7 years before the crash, on June 2, 1978, this same aircraft, JA8119, experienced a serious incident. Landing at Osaka, the plane's tail struck the runway. A tail strike happens when the aircraft's rear fuselage or tail contact the ground, usually because the nose is pitched up too high during landing or takeoff. In this case, the impact was severe enough to damage a critical internal structure, the rear pressure bulkhead. The rear pressure bulkhead is like the lid on the back of a pressurized tube. When an aircraft climbs a cruising altitude, the cabin is pressurized. The air inside is kept at a higher pressure than the thin air outside. That pressure pushes outwards in all directions, and the bulkheads at the front and back of the pressurized section keep it contained. If that rear bulkhead fails, the consequences can be catastrophic. Inspectors discovered the tail strike damage, and the aircraft was sent to Boeing's facility for repair. The job required precise adherence to a detailed repair procedure, the kind of structural work where no shortcuts are allowed. But in this case, something went wrong. Boeing's repair design called for a doubler plate, a kind of reinforcing patch, to be attached to the damaged section of the bulkhead using 2 continuous rows of rivets. Those 2 rows were essential. Together, they were meant to spread the loads and prevent high stress from concentrating along any single line. But during the actual repair, the procedure wasn't followed correctly. Instead of using a single large doubler plate with 2 continuous rows of rivets, workers installed 2 overlapping plates. And in one critical area, only 1 row of rivets carried a load where there should have been 2. That subtle difference created a weak point, an area where stress was higher than the metal could safely tolerate over the long term. Every time the plane took off, climbed, pressurized, and then descended into pressurized, that area flexed. Over time, microscopic cracks began to form near the rivet holes. With each flight, those cracks slowly grew. No one could see them. No one knew they were there. From the outside, the repair looked fine, but the clock was ticking. Fast forward to the late afternoon of Monday, August 12, 1985. It was Auburn season in Japan, a traditional holiday period when countless families traveled to visit their hometowns and pay respect to their ancestors. Flights across the country were packed. Japan Airlines Flight 123 was scheduled to depart from Tokyo's Haneda Airport at 6 p.m., bound for Osaka's Atami Airport. The flight time was just 54 minutes. On board were 524 people, 509 passengers, and 15 crew members. The flight will be operated by 3 men on the flight deck. Captain Masumi Takahama, 49 years old, with thousands of hours of flying experience and a solid reputation as a professional pilot. First Officer Yutaka Sasaki, 39, and experienced co-pilot flight engineer Hiroshi Fukuda, 46, responsible for monitoring the aircraft systems to iron the cabin. A team of flight attendants prepared for a busy domestic sector, helping passengers find their seats, stowing luggage, reassuring nervous flyers, and settling children. Passengers included office workers returning to Osaka, families traveling for the holidays, business travelers, and even a few well-known figures in Japanese society. For nearly everyone on board, it was just another short domestic flight. Many had probably flown this route many times before. Flight 123 pushed back from the gate later than scheduled, departing Haneda at around 6:12 p.m. The departure itself was unremarkable. The 747 SI accelerated down the runway, lifted off, and began climbing into the hazy evening sky over Tokyo Bay. Air traffic controllers cleared the flight to climb to its cruising altitude, 24,000 feet. Inside the cabin, the seatbelt signs were on, engines humming steadily. Some passengers looked out at the coastline and the sea. Others read newspapers, talked quietly, or closed their eyes for a quick rest before arrival in Osaka. They had no idea that a structural failure, years in the making, was less than 15 minutes away at approximately 6:24 p.m. as Flight 123 climbed through about 24,000 feet. Something inside the rear of the aircraft finally gave way. The fatigue cracks that had been growing in the incorrectly repaired rear pressure bulkhead reached a critical size. Under the stress of the pressurized cabin, the metal could no longer hold. The bulkhead ruptured. Pressurized air inside the cabin exploded into the unpressurized tail area with massive force. That force tore through the rear fuselage, blowing off a large section of the tail. Along with the structure, most of the vertical stabilizer, the upright fin at the back of the plane, was ripped off. Inside the tail, 4 separate hydraulic lines ran close together. These lines carried high-pressure hydraulic fluid that powered the aircraft control surfaces, the rudder, elevators, ailerons, and other essential components used to steer and stabilize the plane. When the tail section failed, all 4 of those hydraulic lines were severed. In an instant, Flight 123 lost nearly all of its ability to control the aircraft. For the passengers and cabin crew, the first sign of catastrophe was a violent bang and a deep shudder through the airframe. The cabin rapidly depressurized. Oxygen masks dropped from the overhead panels. Loose items flew through the air. Some passengers later described the sound as an explosion or a huge burst, followed by roaring wind. Flight attendants shouted to passengers to put on their oxygen masks and fasten their seatbelts. In those first chaotic seconds, many people had no idea what had happened, only that something was very, very wrong. In the cockpit, a wave of warning lights and alarms suddenly flooded the panels. Captain Takahama and his crew were confronted with multiple, simultaneous failures. The aircraft experienced a rapid decompression. The autopilot disengaged. The plane began to oscillate, pitching up and down, rolling side to side. The crew's instruments indicated problems with the hydraulic systems, more than one. Controls that normally felt firm and responsive suddenly became heavy or didn't respond at all. At first, the crew didn't know exactly what had happened. There was no automatic warning that said bulkhead failure or tail loss. Instead, they saw the symptoms: decompression, system failures, and unstable flight. Standard procedure in a decompression event is to begin an emergency descent to a lower altitude where passengers and crew can breathe without supplemental oxygen. But almost immediately, the crew discovered that they had far bigger problems than just losing pressure. Their primary flight controls simply weren't working. They tried to move the control column to adjust pitch. The aircraft barely responded. They tried to use a rudder. Nothing. The Boeing 747 had multiple redundant hydraulic systems, designed so that the loss of one, or even two, would still leave the aircraft controllable. But what no one had fully anticipated, and what almost no one had ever seen before, was the loss of all hydraulic systems at the same time. That's what had just happened to Flight 123. With all four hydraulic systems cut near the tail, the control surfaces, the rudder, elevators, and some of the ailerons were effectively dead. In most aircraft, including the 747, the pilot's control columns and pedals don't directly move the surfaces. Instead, they move hydraulic valves that direct pressurized fluid to powerful actuators. No pressure, no movement, no control. Flight 123 was now a 400-ton aircraft flying through the sky with almost no conventional way to steer without stable control. The aircraft entered what's known as a phugoid oscillation. Imagine throwing a paper airplane. It might climb and slow down, then pitch down and dive, gathering speed, then climb again, repeating that cycle. That's a rough idea of a phugoid. Flight 123 began to do this on a massive scale. Climbing, then losing speed, then descending and picking up speed, then climbing again. At the same time, the aircraft also experienced a Dutch roll, a side-to-side swinging and rolling motion that can feel like a slow, rhythmic wobble. From the passenger's perspective, the plane began to lurch, rise and fall, and gently, then more violently, sway from side to side. Inside the cockpit, the crew fought to regain control. Although the hydraulics were gone, the engine still worked. And in this desperate situation, the only way for the pilots to influence the aircraft's attitude was by adjusting thrust. Increasing thrust on both wings could cause the nose to pitch up slightly. Reducing thrust could allow it to pitch down. Adding more power on one side than the other could induce a slow turn. This was imprecise, delayed, and extremely difficult, like trying to steer a ship by adjusting only the speed of its engines, with a broken rudder and no steering wheel. But it was all they had. Captain Takahama and First Officer Sasaki began trying to fly the plane using only engine power, working with flight engineer Fukuda to manage systems and monitor what little feedback they had. Their goal was clear: stabilize the aircraft, turn back, and somehow get to an airport. Shortly after the decompression and loss of control, Flight 123 made contact with air traffic control. The flight crew reported control problems and declared an emergency. They requested to return to Haneda. Controllers, initially unsure of the full extent of the situation, began clearing other traffic and giving heading and altitude instructions. But almost immediately, it became clear that Flight 123 couldn't reliably follow those headings, not in the way a normal aircraft could. The 747 oscillated up and down, yo-yoing between altitudes. At some points, it climbed above 24,000 feet. At others, it descended to below 20,000. The crew struggled to keep it from entering a more severe dive. The plane's path became erratic, curving, looping, and turning, at times heading toward the open sea, at other times back toward land. Controllers tried to vector the flight toward Nagoya and Osaka options, then back to Haneda. But the crew's ability to follow instructions was severely limited. They were barely managing to keep the aircraft airborne. Inside the cockpit, the pilots were under unimaginable pressure. They had an aircraft full of passengers, no normal controls, and only seconds at a time when the jet's attitude and altitude were within anything like a safe range. Every adjustment of the throttles had a delayed, sometimes unpredictable effect. Too much power at the wrong time, and the nose might pitch up too steeply, risking a stall. Too little, and the aircraft might drop into an unrecoverable dive. People on the ground would later report seeing a large airliner flying strangely, climbing and descending, banking in broad arcs, its tail looking odd or incomplete. For many, it simply appeared as a distant silhouette, but some noticed that parts of the vertical tail seemed to be missing. Japan Air Self-Defense Force radar operators, tracking the 747's unstable flight path, understood that something very serious was unfolding. The word spread. A JAL jumbo jet was in grave trouble. While the crew in the cockpit fought to keep the aircraft in the sky, hundreds of passengers in the cabin lived through 32 minutes of terror. The initial decompression had been frightening enough. But now, the irregular flight path turned that fear into a drawn-out ordeal. The plane rose and fell, sometimes suddenly. Overhead bins popped open. Luggage tumbled out. The aircraft swayed. People were thrown against seat belts, some against the ceiling if they weren't strapped in. Flight attendants did what they were trained to do, moved through the cabin as best they could, checking on passengers, reinforcing seat belts, trying to project calm even as the plane lurched around them. They themselves must have been terrified, but many continued to help others. As the minutes wore on, some passengers began to realize the severity of the situation. The flight was not stabilizing. The aircraft was not returning quickly and smoothly to an airport. Instead, it seemed to wander, its movements increasingly erratic. Amid the fear and chaos, some passengers took out pens and paper, anything they could find, and wrote final messages to their loved ones. These notes, found later among the wreckage, spoke of love, regret, instructions, and farewells. Some apologized for not coming home. Others asked their families to live on and be strong. Many of the messages were simple and heartbreaking. Thank you for everything. I love you. We will not quote them directly here out of respect for the families, but they remain some of the most poignant artifacts recovered from any aviation accident, the last words of people who understood that they might not survive, but still thought first of those they would leave behind today as the situation with Flight 123 evolved. The Japan Air Self-Defense Force scrambled fighter jets to intercept and visually assess the troubled airliner. An F-4 Phantom was dispatched, climbing to locate the 747. But timing, distance, and the aircraft's erratic path made interception difficult. The fighter eventually made contact, seeing the damaged jumbo jet from a distance, but by then, Flight 123 was already descending toward mountainous terrain. There was little the fighter crew could do beyond observe. In a matter of minutes, the situation would go from desperate to UN recoverable to as the unstable flight continued. Flight 123 drifted to the northwest of Tokyo, over the rugged mountains of Gunma Prefecture. Instead of leveling out near an airport, the aircraft remained trapped in its deadly cycle of climbs and descents. At times, the crew managed to bring the nose up and avoid a steep dive. At other moments, the aircraft ascended dangerously close to the terrain below. They were running out of altitude and time. The pilots continued to struggle with engine thrust-only control, trying to coax the aircraft toward flatter land, trying to avoid the mountains that were now looming beneath them. But the damage to the tail and hydraulics, combined with the aerodynamic instability caused by the missing vertical stabilizer, created forces that no pilot, no matter how skilled, could fully overcome. At approximately 6:56 p.m., after 44 minutes of flight and roughly 32 minutes after the structural failure, Japan Airlines Flight 123 descended into the mountains near Mount Osutaka. The aircraft, in a nose-high, right-wing-low attitude, struck the ridge of Mount Takamagahara and disintegrated. 520 of the 524 people on board were killed. Only 4 survived. The world's deadliest single-aircraft accident had just occurred. The crash site lay on a steep, heavily forested ridge near Mount Osutaka, in Ueno, Gunma Prefecture, rugged terrain, difficult to access even by foot. Soon after impact, the wreckage burned. The sound of the explosion and flames echoed through the mountains, heard by residents in nearby villages. Reports of a large aircraft crashing began to reach authorities. Search and rescue operations were initiated, but coordination was slow and complicated by nightfall, terrain, and uncertainty about the exact location of the crash site. A U.S. Air Force helicopter from Yokota Air Base, responding to Japanese requests, located the crash site that night. Its crew spotted fires and what appeared to be debris scattered across the slope. According to later reports, the U.S. crew were prepared to attempt a landing or to lower rescues by hoist. But Japanese authorities, coordinating their own response, reportedly instructed the helicopter to withdraw and allow Japan's own rescue teams to lead the operation. On the ground, some responders were reluctant to send teams into difficult, potentially dangerous terrain in the dark, particularly if there was doubt about whether anyone could have survived such a massive impact and fire. The decision was made to delay full-scale search and rescue efforts until morning. This decision would later become one of the most bitterly debated aspects of the entire tragedy. Against all odds, there were survivors. 4 people, all female, survived the initial impact and the aftermath. They found themselves amid twisted metal and wreckage on a steep mountainside, surrounded by the remains of the aircraft and the terrible reality of what had just happened. They were injured, disoriented, but alive. Some could hear helicopters overhead that night, the rotors thumping faintly in the darkness. They hoped rescue was imminent, but no rescuers came. The night was long, cold, and terrifying. The 4 survivors were a 12-year-old girl, Keiko Kawakami, mother, Hiroko Yoshizaki, and an 8-year-old daughter, Mikiko, and a 26-year-old flight attendant, Yumi Ochai. Some were trapped in a section of fuselage that had come to rest in such a way that it protected them from the worst of the impact forces and post-crash fire. They later described hearing the cries of other survivors in the hours after the crash, voices that gradually fell silent as the night wore on. By morning, only these four remained alive. At First Light on August 13th, full-scale search and rescue teams finally began to converge on the crash site. Helicopters circled above the wreckage. From the air, the scene was devastating. Large sections of the fuselage torn apart, scattered over a wide area. Trees were shattered and burned. Smoke still rose from smoldering debris. Rescue personnel rappelled down into the site, carrying stretchers and medical supplies, hoping, but not necessarily expecting, to find survivors. To their astonishment, they did. Rescuers found the four survivors in a relatively intact section of the aft fuselage, shielded to some extent from the worst of the destruction. They were injured and traumatized, but conscious. As they were carefully extracted and airlifted to hospitals, the scale of the overall tragedy became clearer. Out of 524 people on board Japan Airlines Flight 123, only 4 had survived. The vast majority had died instantly in the impact. Others, investigators later believe, might have survived the crash but succumbed during the long hours before rescue arrived. This possibility intensified public anger and grief, fueling questions about whether a faster nighttime response could have saved more lives. News of the crash and the staggering death toll shook Japan to its core. The country had experienced aviation accidents before, but nothing on this scale. Families gathered at airports and hospitals, desperate for information. JAL officials held press conferences, often with visible emotion. The media broadcast images of the crash site and reported on survivors' stories, the farewell letters found among the wreckage, and the questions now swirling around Japan Airlines, Boeing, and the government. Public grief was intense, matched only by a demand for answers. How could a modern airliner, flying a short domestic route, with experienced crew and normal weather, simply fall out of the sky? The answer would lie not in the weather, or in pilot error, but in a neglected repair and the long, silent work of metal fatigue. The official investigation into the crash of Flight 123 was led by Japan's Aircraft Accident Investigation Commission, with participation from Boeing, the U.S. National Transportation Safety Board, NTSB, and other experts. The task ahead of them was immense. The crash had occurred in difficult terrain. Wreckage was scattered across a wide area. Fires had consumed parts of the structure, and the aircraft had broken into many pieces, complicating the reconstruction of exactly what had happened and in what order. But from the early stages, one striking detail stood out immediately. The vertical stabilizer, the large tail fin, was almost entirely missing from the main wreckage site. Investigators soon found parts of it kilometers away from the main impact area. This suggested that it had separated from the aircraft in flight sometime before the final crash. The question was, why? Investigators recovered the Flight Data Recorder, FDR, and Cockpit Voice Recorder, CVR, the so-called black boxes, actually bright orange for visibility. The FDR held various parameters: altitude, airspeed, heading, control surface positions, and more. The CVR captured the last 30 minutes of cockpit audio. Together, these devices would provide a crucial piece of the puzzle. The recording showed a normal departure, followed by a sudden decompression, alarms, and then a long period in which the crew fought to control the aircraft using every means at their disposal. The CVR captured their confusion as they tried to understand what had failed, their growing realization that they had little or no control authority, and their ongoing attempt to coordinate with air traffic control while trying to save the aircraft. Importantly, the recorders indicated that the crew remained conscious, engaged, and fighting for control right up to the final moments. There was no evidence of pilot incapacitation. Attention turned increasingly to the aircraft itself. Investigators painstakingly collected pieces of the rear fuselage and pressure bulkhead, laying them out in a hanger like a giant, deadly jigsaw puzzle. They noticed telltale signs of structural failure and metal fatigue around the rear pressure bulkhead. Rivet holes showed evidence of cracks that had grown over time. It became clear that this bulkhead had not simply failed from a single overload event. It had suffered a progressive, fatigue-related failure, one that had likely been building for years. As they studied the pattern of damage, investigators realized that the repair performed after the 1978 tail strike was central to the failure. Further examination of maintenance records and Boeing documentation confirmed it. The repair had not been carried out in accordance with Boeing's original design. The investigation found that the 1978 repair of JA-8119's rear pressure bulkhead had been improperly executed. Where Boeing's original engineering repair manual called for continuous doubler plate with 2 rows of rivets, the actual repair used 2 overlapping splice plates, and for a crucial section, only a single row of rivets carried the load. This created a weakness, a zone of abnormally high stress where the metal was more likely to develop fatigue cracks under repeated pressurization cycles. Computer analysis and laboratory testing showed that these fatigue cracks would grow incrementally with each takeoff and landing. Over the approximately 7 years and thousands of flights since the repair, the cracks had slowly extended, eventually reaching a critical length at which the bulkhead could no longer sustain the internal pressure loads. When the bulkhead finally ruptured on August 12th, it did so explosively, sending pressurized air rushing into the tail, tearing open the aft fuselage, and ripping off the vertical stabilizer. The loss of the tail structure simultaneously severed all 4 hydraulic lines routed through that area. It was a chain of events that could be traced back, step by step, to that incorrect repair 7 years earlier. The investigation concluded that Boeing, as the aircraft manufacturer and the party that had performed the bulkhead repair, bore significant responsibility. The repair had deviated from the approved design. In essence, a critical safety barrier, the integrity of the rear pressure bulkhead, had been compromised by human error in the repair process and compounded by inadequate quality control. Once installed, the improper repair was not detected in subsequent inspections. The fatigue cracks grew silently, hidden beneath fittings and structure, until they reached a breaking point. The Japanese accident report placed primary blame on the faulty repair. For Boeing, this was a grave finding. The company publicly accepted the conclusions, expressed regret, and moved to review and strengthen its repair and inspection procedures. Crucially, the investigation also examined the actions of the flight crew. In the immediate aftermath of the crash, as often happens, there were whispers and speculation. Had the pilots made some critical mistake? Could they have handled the emergency differently? The data told a clear story. The crew of Flight 123 fought bravely and skillfully in an almost impossible situation. With no hydraulic control and severe structural damage, they faced a scenario for which there were no real precedents, no checklists, and almost no training scenarios. They attempted to descend to a breathable altitude after the decompression. They tried multiple times to control pitch and roll. Eventually, they discovered that engine thrust modulation was their only usable tool. Using throttle-only control, they managed to keep the aircraft airborne for more than 30 minutes, an extraordinary feat considering that, in later years, other aircraft that lost all hydraulics, such as United Airlines Flight 232 in 1989, were also nearly impossible to control. The investigation concluded that the pilots did as much as could reasonably be expected, and more under the circumstances. In Japan, the captain and crew came to be viewed not as culprits, but as heroes who fought to the end to save their passengers. Although Boeing's incorrect repair was central to the technical cause of the crash, Japan Airlines was not exempt from scrutiny. Questions were raised about JAL's inspection and maintenance regimes. Could the fatigue cracks have been detected? Were inspections thorough enough? Had there been missed opportunities to spot structural anomalies in the tail section? JAL's leadership faced intense public anger and grief. The airline's president resigned, taking responsibility for the disaster under the principles of corporate accountability that run deep in Japanese culture. One senior JAL maintenance engineer, associated with oversight of the aircraft condition, took his own life in the aftermath of the crash, leaving notes expressing remorse. The tragedy became not just a technical investigation, but a national reckoning about safety, responsibility, and the price of failure in a high-reliability industry. Beyond the technical cause, one subject continued to haunt families and the public: the delay in rescue operations. The presence of potential survivors at the crash site during the night, combined with reports that a U.S. helicopter had located the site but was told not to intervene directly, triggered widespread anger. Could more lives have been saved if rescuers had gone in immediately, despite darkness and rough terrain? The official position was that the terrain was dangerous, the exact number of survivors unknown, and nighttime rescue could risk additional casualties among rescuers. But to families who learned that loved ones may have survived for hours after the crash, these explanations were deeply unsatisfying. In response, Japan reviewed and improved its emergency response protocols, interagency coordination, and nighttime search and rescue capabilities. The memory of Flight 123 would forever influence how future disasters were handled. The legacy of Flight 123 extended far beyond Japan. Regulators and airlines around the world took a hard look at their structural inspection programs, especially for aging aircraft and for high-cycle jets like domestic 747s and other short-range workhorses. Several key changes emerged from the lessons of this tragedy. 1. Stricter oversight of structural repairs. Investigators emphasize that repair instructions from manufacturers must be followed meticulously, especially for critical structures like bulkheads, spars, and pressure vessels. Regulatory authorities around the world reinforce requirements for strict adherence to approved repair documentation, detailed documentation and traceability of major structural repairs, independent inspections and sign-offs, especially on critical safety components. Boeing and other manufacturers updated their repair manuals, issued bulletins, and re-examined past repairs on similar aircraft to ensure that no other planes had been given similarly flawed fixes. 2. Enhanced non-destructive testing, NDT. Non-destructive testing methods, such as ultrasonic testing, radiography, X-ray, and eddy current inspection, became more widely applied and standardized. The industry recognized that visual inspections alone were not enough to detect hidden fatigue cracks in critical areas. Airlines and maintenance organizations invested in more sophisticated NDT equipment and training, especially for high-stress areas in previously repaired zones. 3. Aging aircraft programs. Flight 123 highlighted the long-term effects of repeated pressurization cycles and the importance of age and cycle-related maintenance. Regulators began to formalize aging aircraft programs that identified components particularly susceptible to fatigue, mandated special inspections and life-limited parts, required periodic structural reviews and modifications for older airframes. These programs aimed to prevent time bombs, hidden structural weaknesses, from silently developing over years of service. 4. Emergency response and SAR improvements. The delays in rescue operations for Flight 123 led Japan to improve coordination between civilian authorities, self-defense forces, and foreign military assistance, enhance night vision capabilities and training for mountain rescue, develop clearer criteria for launching immediate, high-priority rescue efforts even in challenging terrain or conditions. The idea was simple. When lives may still be at stake, time is critical to end the decade since the crash. The site near Mount Osataka has become a place of pilgrimage and remembrance. Families of the victims, former JL employees, locals, and visitors from around the world hike up the mountain trail to pay their respects. Monuments and memorial markers bear the names of those lost. Every year on August 12th, memorial ceremonies are held to honor the victims of Flight 123. Relatives share stories of their loved ones, parents, children, siblings, colleagues, friends, whose lives ended on that ordinary Monday evening in 1985. Many carry with them the weight of what IFS and might have beens. They also carry something else, the determination that such a tragedy should never be repeated. The 4 survivors of Flight 123 went on to live their lives under the shadow of extraordinary trauma and public attention. Some eventually shared parts of their experiences. Others maintained privacy. Their survival was both miraculous and burdened, a mixture of gratitude, survivor's guilt, and the challenge of living with memories that many would find unbearable. Their accounts helped investigators understand the sequence of events in the cabin and the nature of the crash. But beyond that, their existence serves as a powerful reminder. Even in the worst of disasters, there can be threads of hope and resilience. Today, commercial aviation is statistically one of the safest forms of travel ever created. That safety is not an accident. It is the product of countless lessons learned from tragedies like Flight 123. In a strange, painful way, each disaster has contributed to making the system safer for everyone who flies today. The story of Japan Airlines Flight 123 underscores several critical truths. 1. Small errors can have enormous consequences. The incorrect installation of a repaired double plate, the misplacement of a row of rivets, on their own, these might have seemed like minor deviations. But in a highly engineered system like an airliner, small deviations can lead to new stress points, fatigue, and eventual catastrophic failure. It's a sobering reminder of why absolute precision and adherence to procedures are essential in safety-critical work. 2. Redundancy has limits. The Boeing 747 was designed with multiple hydraulic systems to ensure that the loss of one or even two would not be fatal. Yet the physical routing of all four systems through the same vulnerable area at the tail meant that a single, unexpected structural failure could sever them all. This forced engineers and regulators to think not just about redundancy on paper, but about common mode failures, scenarios where multiple redundant systems can be knocked out by a single event. 3. Human courage in impossible situations. The crew of Flight 123 faced a scenario for which there was no straightforward solution. Yet they fought for over half an hour to keep an almost uncontrollable aircraft in the air, using only the throttles, trying to bring their passengers safely back to the ground. Their efforts, while ultimately unsuccessful in saving most lives, nonetheless gave the four survivors a chance. Their actions are studied today as an example of extraordinary airmanship under nearly impossible conditions. 4. Rescue time matters. The night that followed the crash raised difficult ethical and operational questions. When is it too dangerous to send in rescuers? When does the potential to save lives outweigh the risks? Flight 123 forced emergency planners to confront these questions and improve their readiness for high-stakes, high-uncertainty situations. Since 1985, aviation technology has advanced dramatically. New airliners are built with composite materials, advanced systems monitoring, and more sophisticated redundancy. Structural analysis and fatigue modeling are far more advanced. Maintenance tracking is digital and interconnected, yet the fundamental truths remain. Aircraft still rely on the integrity of their structures and the precision of their repairs. They still depend on human judgment, both on the ground and in the air. They still operate in a world where rare, unexpected failures can test every assumption. The legacy of Flight 123 is written not just in engineering changes, but in a deepened awareness throughout the aviation community of how fragile safety can be and how hard we must work to preserve it. When we look back at August 12, 1985, we see more than a sequence of mechanical failures and human actions. We see a full aircraft of individual lives, each passenger's story, each one with family, friends, dreams, fears, joys. We see crew members who went to work that day expecting a routine flight, and instead face a battle no simulator had fully prepared them for. We see maintenance personnel and engineers, most of whom took pride in their wake, now confronting the devastating consequences of a critical error made years before. We see rescuers who had to make impossible decisions in the dark, later judged by the harsh light of hindsight. And we see a nation and an industry forced to confront how much it costs when safety systems fail today. More than 3 decades later, Japan Airlines Flight 123 is still studied in aviation schools, flight safety courses, engineering programs, and emergency response training. For the families of the victims, it is not just a case study, it is a personal loss that never completely fades. On the mountain, the wind still blows over the memorials at Osutaka. Visitors still climb the trail, some carrying flowers, some carrying only memories and questions. In those quiet moments, the statistics fall away. The technical diagrams fade. What remains are the people, the 520 lives cut short, and the 4 lives that continued, forever marked by that night. Japan Airlines Flight 123 was more than the world's deadliest single aircraft accident. It was a turning point, a harsh lesson about the importance of meticulous maintenance, structural integrity, and robust emergency response. It showed us that even the most advanced machines can fail if small errors go unchecked, that even the most carefully designed systems can be vulnerable in ways we don't fully anticipate, and that, in the face of disaster, human courage still matters, in the cockpit, in the cabin, and on the ground. For everyone who flies today, the safety we often take for granted has been built, in part, on tragedies like this one. We owe it to those who lost their lives on Flight 123, and to their families, to remember what happened, to learn from it, and to keep pushing for a world where such accidents become ever more rare. I'm Johnson. Thank you for joining me as we revisited the story of Japan Airlines Flight 123.